So first I want to thank the Clay Institute for giving me the opportunity to speak here. So historically, I mean, there is a deep interaction between complex differential geometry and algebraic geometry. So today I want to present one of this recent progress along this direction. So my first part, I will introduce this Kähler-Einstein and K-stability, these notions. So if X is a compact complex manifold, now G is a Hermitian metric on X. So I think in 30s, Kähler introduced this kind of metric, now called the Kähler metric. So basically, locally, it can be written as this kind of form with some like a smooth function. And we know this is true if and only if that the associated Kähler form is a closed form. Then actually in the original paper where Kähler introduced this Kähler metric, he already asked this question, which was later promoted by Calabi, is that find the Kähler metric omega on your complex manifold such that the rich omega is equal to lambda omega. Here lambda is some constant. And this cannot hold for any complex manifold. Actually, if you take the class of this equation, you realize that the left-hand side, it's all, no matter which omega you choose, it's always a first Chern class. So this equation says the first Chern class is proportional to your Kähler class. So in other words, the Chern class has to have a psi. So in the dimension 1, of course, this is just a consequence of the uniformization theorem. And when lambda is equal to 0 or equal to 1, I mean, there's a famous theorem by in lambda 0 case by Yao and lambda -1 case independently by Aban and Yao, but in 70s. But today we are going to focus on the case when lambda is equal to 1. In other words, the Chern class is positively proportional to a Kähler class. So we call such kind of manifold, the Fano manifold after Italian mathematician Gino Fano. And we know that actually this cannot be always true. So in 50s, Matsushima already found that there is an obstruction, say that X has Kähler-Einstein, will imply that the autonomial group of X is always reductive. So, but you can easily write down examples, even in dimension 2, that the Fano manifold whose autonomial group is not reductive. So our goal then is characterize precisely when rich omega is equal to omega at your highest solution. In other words, characterize precisely when a Fano manifold admits a Kähler-Einstein metric. But this is, you can consider this as a different geometry problem, but there is a somewhat more ambitious program is basically parameterize them using good modular space. So here good, I mean, is just a vague term, but later it will become a mathematical term. So today I will focus more on the algebraic side of this problem, which has multi-facets. It relates to different geometry, PDE, and algebraic geometry. So today I will focus on algebraic geometry side, but I will start with some differential geometry development. So basically, now we are trying to find the omega, which the class now is fixed because we want the class is basically is C1. So now we just vary omega in the same class to find whether we can solve this Kähler-Einstein equation. And by D-bar lemma, we know that adding two such kind of metric, the difference can be written as D-bar phi for some smooth function phi. And so if I start with any metric within this class, then in other words, I want to find the phi such that this equation can be solved. Because omega 0 is inside this class, so we know that omega minus omega, rich omega 0 is, you apply d-bar lemma to this, we know it's a d-bar of some smooth function. Then to solve this omega, in other words, to solve this phi, it's equivalent to solve this kind of Monge equation, which is of this kind of form. And of course, when we want to solve some like a PDE, the standard way is we try to find the functional and try to set set the functional in a way that the Euler-Lagrangian equation of the functional is the equation here. Here, for this reason, Mabuchi in 1806 found a K-energy function with this property. So basically, the critical points of this functional will correspond to the solution to this complex Monzon-Pei equation. So in other words, if you can find the critical point, then the Kähler-Einstein problem is solved. So we want to characterize for what kind of complex manifold, Fano manifold, this Mabuchi functional has a critical point. So let's look at the finite-dimensional Toy model. So here we consider a G, which is a complexification of a compact group. Here K is a compact group. And G acts on some like a polarized manifold XL. And so because K is compact, we can always find the K invariant norm on L. And now I set up a function, which first I fix the point X. I choose any lifting of this X hat on this line bundle. And we define a function in a way on G mod K, such that in a way that for any point G in this group, I use G to act on this lifting. And I look at the norm, I take a log. So because the norm is K invariant, this function is automatically defined on G mod K. So now we want to ask ourselves when this function has a minimum. So this is a finite-dimensional problem. We have a finite-dimensional space. We have a function. We want to ask ourselves when this has a minimum. So here we know that if I take a C star mapped to this G mod K, it will give a geodesic here. And if I take this geodesic acts on this, so here should be X hat. And then I take a derivative of that, then it's going to be some algebraic quantity. This algebraic quantity is precisely the limiting point of this X. Then this line bundle represents this limiting point. Because this point is a C star fixed, then the C star acts on this line bundle. It has a weight. This weight is precisely this limiting point. In other words, this algebraic quantity is the derivative under the infinite place. So with this observation, now we know that if X has a unique minimum, then with some analysis, you can show that basically that's equivalent to saying when you go along your point, go to infinity, then the derivative under the infinity should be positive. So if you can show that, then you can show there is a unique minimum. But so all the derivative is, all the geodesic is given by C in this Lie group with a real coefficient. But then there is an equivalence somewhat, mysterious that to say for the weight, for the derivative positive along all the real direction, it actually suffices to the derivative is positive along all the rational direction. And by our remark above, the rational direction is actually an algebraic quantity, which is the weight of the action of C star. So we have this equivalence here, which, and then somewhat more remarkably, this condition is the so-called Hilbert-Mumford condition. So with this, we know that that's equivalent to say X is geometrically invariant theory stable in this action. So somehow to summarize, we have this equivalence between that this F has a unique minimum to that the X is actually can be parameterized in some moduli space. But to get this equivalence, there are 3 steps. So the first step is somewhat like an analytical step, and then the second step is kind of say that this like a look at all the real direction is equivalent to look at all the rational direction, which here follows from the fact that we are doing some like algebraic geometry in finite dimensional space. And then the last step is the step that the positive of the rational direction is actually equivalent to it's parameterized by moduli space. So it's actually precisely these 3 steps we want to generalize to our infinite dimensional problem. Okay, so let's first start with some analytic intuition of how to find the right algebraic notion. So I think in 18th, Yao already had the idea that the existence of Kähler-Einstein metric on a Fano manifold should relate to some kind of algebraic stability. But in his time, he probably know that the algebraic stability involved is not the GIT stability. But that time he probably didn't know what was the right notion of algebraic stability here. But in 19th, Ding Tian and Tian, they made a calculation that if I start with my Fano manifold, I embed into some Pn. And then I use a C star to act on my Fano manifold. And then I look at what happens under this C star. So they calculate, they pull back, along this line, they pull back the Fubini-Studio metric. And then, so you get a parameter of a metric. Then they use Mabuchi function, acts on this metric. Then they take a derivative. Then they realize unto the infinity, this derivative is some quantity called a Futaki invariant. And then if you have a unique Kähler-Einstein metric, which means you have a unique minima of this Mabuchi functional, will imply that, again, the derivative unto the infinite place will be positive. Otherwise, you can think unto the infinite place, the functional will go to negative infinity. So this way, they show that they define this term, and they show that the existence of Kähler-Einstein metric will imply this positivity of this Futaki invariant. And later, Tian actually defined the stability, he called K-sim stability, basically using this quantity. But here, the upshot is he has to consider all the degenerations. So basically, it's not enough to just consider one embedding of X into Pn. So you have to consider simultaneously all possible embedding of X into larger and larger Pn. And in each Pn, you consider all the one-parameter subgroup. So this is not a finite dimensional problem under this level. So it's an infinite dimensional problem. And Donaldson later realized this Futaki invariant, which was defined analytically in the original paper, can be defined algebraically. And because of this algebraic definition, it actually can be further generalized. So then the so-called Yao-Tian-Donaldson conjecture, or YTD conjecture, now is a theorem says for Fano variety, it has a Kähler-Einstein metric if and only if it's K polystable. So here I'm not going to say too much about the polystability, but the stability just means there is a unique. I mean, if you change it to at least a unique Kähler-Einstein metric, then you can say if and only if this is K stability. So I want to explain this theorem in the next part of my talk. So, but again, I will concentrate on the algebraic progress of the story. So somehow, I think at the beginning, people used the framework of geometric invariant theory to study this problem. But it was realized around 2010 that actually maybe the right geometrical framework is not the geometric invariant theory, but the higher dimensional geometry, or the theory developed around the so-called mean-model program. And that's what I'm going to explain. So first, I want to explain some like early progress. So in around 2011, Odaka realized that the notion of K stability of a variety will actually imply the variety has certain of singularity. This singularity appeared in minimal program. So I think that, as far as I know, this was probably the first time people noticed that the stability from this Kähler-Einstein problem is related to some notion from bidirectional geometry. And then Chi and myself, we initiated something called to study the special objects. So we basically prove that you don't have to consider all test configurations. You only need to consider the C-star degeneration to some kind of special object. And this was conjectured by Tian, because basically TM conjecture, his definition is equivalent to Donaldson's, and this result give the proof of that. But actually, I think the probably more striking is that somehow this minimum program really start to play some, because this result was completely proved using minimum program. So somehow the minimum program really start to play a role in this theorem. And another observation made by Berman was he introduced the notion called Dean stability. So basically, in an early paper by Dean, he noticed that you can replace the Mabuchi functional by something called the Dean functional. And the critical point of Dean functional will also give you Kähler-Einstein metric. But somehow the Dean functional needs less regularity from the analytical side. And then Berman basically built up the so-called Dean invariant from this Dean functional, like the Futaki invariant from the Mabuchi functional. And then Fujita realized that this Dean stability is actually just equivalent to K stability. So you can replace, for Fano variety, so you can replace everything using K stability by just using Dean stability. But the Dean stability has a better property. It actually has like a better approximating property. So this is an analog to the fact that the Dean functional needs less regularity in the analytical theory. So in the algebraic side, so this Dean invariant actually just has better approximating properties. So, but what's crowned the early development is this like a valuative criterion. So here I have to define some terms. So for any variety X, I consider some birational model, and I consider divisor on this birational model. Then I can look at this difference between the canonical class of X and Y. And it will have some like a vanishing order, like the vanishing order of the Jacobi along this divisor. And then plus 1, that's called the log discrepancy. I mean, this quantity appears in minimal program a lot. And basically, this is the only way we can control the singularity along the minimal program process. And here, if this quantity is positive for any divisor E, X is called a Karl-Marx log terminal singularity. And I mean, if you don't know this notion, that's fine. You just think about this is some invariant on singularities. And another quantity is expected vanishing order. So basically, if I look at the minus kx, I look at how much it vanished along t, then asymptotically, it will be some like a volume here. Now I take the integral of all the volume, and I divide by the total volume. Then that's just expected vanishing order Sx. So, but the main invariant here is this delta function, which is the infimum of the A divided by S over all the divisor E. So here I want to emphasize the E, you take the infimum over all the possible E, which is on all possible birational models over X. So in other words, it's all possible divisorial valuations over X. And you look at the infimum. And actually, if this delta is less than 1, then it has an analytical meaning. It's equal to the supremum when you try to solve this Kähler-Einstein equation by using the continuity method. So in other words, this delta actually, when it's at least when it's less equal to 1, it's actually, you can easily say its connection with the Kähler-Einstein problem. But one can also completely prove it algebraically that the K stability is equivalent to say that the A over S on any E is positive. So like a few slides ago, I introduced the notion of K stability, but I didn't really give a very precise definition because I didn't define Futaki invariant algebraically. But you can just take this as a definition if that's the first time. But historically, we have to prove this characterization is equivalent to the original K stability definition. And the uniform k-stability just say that the infimum is larger than 1. So of course, you can easily say the uniform implies the k-stability, but a priori it's not the vice versa, because then the theorem we proved together with Liu and Zhuang is that when delta is less than n plus 1 over n. So remember, delta, we are interested in the case basically when delta is around 1, or let's say delta is less than 1 plus epsilon. But we can push the bound a little bit to the, here n is the dimension of x. That as long as the delta x is less than n plus 1 over n, then there exists a divisor E, such that this infimum is always computed as a millimole. So in other words, particularly when delta x is equal to 1, let's just say that the uniform k-stability is actually equivalent to k-stability. And this year will actually also introduce, will give you a degeneration of x to some final variety x0. So together with this analytical result, which says that for any final variety x, possibly singular, then the uniform k-stability will imply the existence of unique Kähler-Einstein metric. So if you put this together, put these two results together, that's like the step 1 and the step 2 in our toy finite dimensional model. So this is like the step 1, that there is you have to just look at all the slope and the infinite place. The positivity there is give you a critical point. And then this is like the second equivalence, that you only need to look at somewhat the rational data, and then that's enough. So if you put these two together, that just implies the k-stability will imply the uniqueness of Kähler-Einstein metric. So here, to get this result, I mean, of course you have to do lots of analysis, but so you have to take some like a completion of the function of the space of potential function, smooth potential functions, and try to develop the geodesic theory there. But today I will just focus on the algebraic side of the story. But before I go further, let me mention that in a smooth case, there is another solution of the same conjecture using Riemannian geometry theory. I mean, this Riemannian geometry theory has lots of contributors, but the key regularity result they prove in this Riemannian geometry theory is that if I take a sequence of Kähler-Einstein Fano manifolds, then the Gromov-Hausdorff limit, which a priori is only a metric limit, is actually a Kähler-Einstein variety. So here, the theorem I just mentioned in the previous slides actually implies the algebraic consequence of this. Say that if I have a sequence of k polystable Fano variety, then it has a unique k polystable Fano limit. So if you compare these two result, the result above, I mean, it actually says something stronger on the matrix. But however, it has to have this smooth assumption. This result doesn't need the smooth assumption. And to construct a moduli space, you will see later that this is very important, because we know that in higher dimensional world, you cannot assume all your varieties is smooth, or even just the limit of smooth one. I mean, the curve, we know that the mg bar is kind of is irreducible. So all the curves you want to parameterize actually comes from as a limit of smooth curves. But in higher dimensional, that's too much to expect. So we really have to deal with non-smoothable object, like the general singular object. I mean, with some like a mild singularity, and this theorem, this algebraic version of this theorem gives that. And this algebraic statement, the technical call is the so-called higher rank finite generation theorem, which I'm going to explain in the next few slides. So, but I want to set up the question. So basically, you can think about this higher rank finite generation theorem is an analog of prove some like a regularity of some weak solution. So somehow we want to show that this remember we want to show the delta is achieved by A over S for some divisor E. But what we want to do is we want to enlarge our space such that we can easily find some a minimizer of A over S of this function on this larger space. And then we try to prove that actually among all these minimizers, there is some divisorial valuation. So this kind of algebraic work is in some sense analog to that you try to solve your PDE. You first found the weak solution and then you prove regularity for that. So now we have to enlarge our space, which is just the space of valuations. I mean, this is very classical. Basically, we just look at all the functions from the non-zero rational function variety to real numbers, and it satisfies the non-Archimedean triangular inequality. And then you can, as I said, you can show that this function A over S can be extended to this larger space, and at least if you assume this like a harmless assumption in our work. And then for each valuation here, we can formulate the so-called associative gradient ring. So basically, this R is the anti-canonical ring. So it's basically the coordinate ring of your Fano variety. And then for each section S in this coordinate ring, you look at the vanishing order along this V. You fix a lambda. So if it's larger or equal to lambda, I say it's in this vector space. And if it's certainly larger than lambda, I say in this vector space. And then I just take this gradient and then put all the OM and the lambda together. It's very easy to prove it's a gradient ring. So this is an associative gradient ring. And the higher rank finite generation theorem, which is the main call to prove the optimal destabilization theorem, is saying that if still with this harmless assumption for us, then if V is a valuation which computes a delta X, then actually it's finitely generated. So somehow this finite generation, as I said, plays a role like a regularization. So once you have this finite generation, it's not very hard to prove that you can either, it's like a 1-2 pages argument to say you can actually perturbate it to find the divisorial valuation. But the upshot is one needs to prove that the minimizer satisfies this finite generation property. And there are two parts of this proof. So basically, first you have to develop some K-stability theory to show that this minimizer should satisfy some Bayesian geometry property. And then you have to develop the Bayesian geometry theory to say that any valuation satisfies this Bayesian geometry property actually is finite generated. So somehow you have to develop both the K-stability side and also the Bayesian geometry side. So here, let me first state the K-stability side. So in other words, I want to find a suitable Bayesian geometry condition and then show that the minimizer satisfies this Bayesian geometry condition. And the next step I will show any valuation satisfies this Bayesian geometry condition actually is finite generated. I mean, it took us a while to formulate the right condition. And now, finally, we understand that the right condition should be this valuation comes from some special model. So here special means that I have this Fano variety X, I have some Bayesian model Y. And I have some like divisor E, such that the Y and the E is a simple normal crossing, at least at the generic point of their intersection. And this Y has some like log Fano structure. So in other words, I can find the divisor delta such that this is ample. And then I just say V comes from this simple normal crossing data. If the V is basically a monomial valuation, if I use the coordinates Y and E. So here, locally around this point, E is given by a bunch of coordinate functions, ZI. And now if I consider valuation V such that for any valuation F, for any function F, I pull back the F along this point, generic point eta, And I take the Taylor expansion here. And then, so I just look at all the non-zero C beta. So for which beta, such as C beta is non-zero, then I look at the minimum of alpha and beta among all these C beta, beta such as C beta is non-zero. So this is just a standard monomial valuation. And what we want to say is if I have a minimizer, it's actually a monomial valuation over some special model. So the key point is it's not a monomial valuation over any model, but it's a monomial valuation over some special model. And then the next, we just prove that for any monomial valuation over any such kind of special model, it's finite generated. Actually, it's stronger that because one can easily prove for this special model, all the possible monomial valuation is basically a simplicial cone. So we actually prove adding two, if you have adding two valuation correspond to points in the interior of the simplicial cone, then the gradient ring is actually isomorphic. So it's not just finite generated, but there are lots of, there are basically finite gradient ring. So if you take a different alpha, essentially only the gradient number is changing a little bit, but the ring is just the same. And if your alpha is a rational vector, which corresponds to divisorial valuation, then this finite generation is already known by minimal program. So then just knowing this fact, of course, adding one is finite generated. Because adding one, you can just perturbate a little bit to some rational one, and you know they have the same gradient ring. And the proof of this, I mean, as I said, if it's rational, then that's just follow from the minimal model program, or more precisely from the result by Berka, Kashini, Hicken, McKernan. But for this higher rank one, you have to develop a new method to prove it. So basically, we prove that there exists a equivalent family. This R is the same R here. So basically, we prove there is an equivalent family acted by some torus group, which is C star power to R, over C power to R. So the action of this group on the base is just a standard action by multiplication. And then we actually prove that the central fiber of this family, the coordinate ring, is precisely just this gradient ring. So in other words, we construct a geometrical model to realize this finite generation. I mean, that's of course always how we prove finite generation in minimal program. We actually construct some geometrical model to realize it. Okay, so next I want to move to the Moduli of Fano varieties. So this is somewhat correspond to the last step, like you have all this kind of positivity of some C star action, this kind of stability, then you want to get a moduli space. So in the GIT, in the finite dimensional toy model, that just comes from the Hilbert-Mumford criterion, but here we need a lot more. So let me just briefly review the history of Moduli of varieties. So of course, this went back to like people like Abel, Jacobi, when they want to parameterize elliptic curves. But for curve of higher genus, which you can consider as the initial point of the algebraic moduli theory, that was basically done by Mumford, but he was using GIT. And later, Mumford, we had this Mumford compactification, MG bar. So that's a curve case. And then we want to generalize the picture to higher dimensional. And we realize that the GIT is not enough. So we have to find some like a new theory to do that. And in 1888, Kohler, Schiffer, Baron proposed the right stability when the variety for kicks is positive. So this corresponds to the Chen class negative case. So basically, in that situation, the right stability for single variety is just this condition plus some singularity condition. So you only need to consider kicks positive one with some right singularity condition. And then when you want to construct this moduli space, a large part of this theory is basically just you have to prove the corresponding result in minimal program. And fortunately, this was all done by the time of 2000 late 10s. So I mean, it's not just the minimal program itself. I mean, we have to also understand what we mean by higher dimensional varieties, a family of higher dimensional variety. So there are other input of this theory, but a large chunk of this input came from the minimal program. But now we want to consider the case of Fano variety. So basically, before 2010, I think very few algebraic geometers really thought about this problem, because I think people just think it's impossible, because there is no natural extrinsic theory. This was true even when the case positive case, the GIT doesn't work. But now you want to apply the minimum program ideal from the, for instance, from the Kähler-Einstein case to this. We applied it. We realized that you can always construct a limit, which is a Fano variety. But the problem is often there are too many of them. So of course you want your moduli space to be Hausdorff. So you want to have one single limit. But if you just post a Fano condition, often there are more than one limit. So of course now we realize the solution is we actually have to consider all the Fano variety as a stack, and then we stratify them. So only in the case semi-stable ones yield the moduli space. So this is a little bit like the moduli space of vector bundles. So if we consider the moduli space of, if we consider the stack of, we can consider the stack of all vector bundles with fixed numerical invariants. But if you want to construct a good moduli space, you have to look at the semi-stable one. So the Fano has, from that viewpoint, is similar to the moduli of vector bundles. So with this in our mind, let's outline the construction, the plan of the construction. So each of these steps, of course, requires a proof, and some of them is actually, the proof is quite challenging, but let's just outline what we want to do. So we fix the numerical invariants, and then we first show that with this given numerical invariance, then there is a uniform M such that the minus mkx embed your Fano variety in the projective space. So only with this condition, you can put all the Fano variety inside the same space. So this is the so-called abundance step. And this step basically is a bidirectional geometry step we know. Then the next step is now if you put them, there is a finite type Hilbert scheme, parameterize all possible candidates, but it could parameterize more. So you want to cut out the locus which you precisely want. So in other words, you want to prove that if you look at the universal family of the Hilbert scheme, then the locus which parameterize what you want is a locally closed locus. So this is the next step. And with those two steps in your hand, then you can, that already tells you your stack is a finite type Artin stack. But then the next one is now, because when you embed your x into Pn, you actually, there is the ambiguity. The ambiguity is, you can choose coordinates. Then you have to module those coordinates. In other words, you have to take the quotient of PGL n plus 1 on this, acting on this Hilbert scheme. Then you take the quotient. This is actually a very subtle step, because when you take a quotient of a variety by a positive dimensional group, I mean, most likely you will get nothing. For instance, you consider the case that you have a C-star group action on C. So if you take quotient, that's fine. That's just 1 point. There's 0 and there's non-zero, but you just identify them. However, if you consider C-star action on CP1, then it's problematic, because there is a 0, there is the infinity. They are very far away upstairs, so you cannot identify them. If you want to construct a meaningful moduli space, you don't want to identify them. But then there is no, but of course they are connected by non-zero C inside. So in other words, there is no meaningful quotient just for CP1 over C star. So even this like very simple case, we don't have a very nice geometric quotient. However, you want to prove in this case, you do have. This is, of course, very much depend on what kind of modular functor you are parameterize. So the fact that actually K-stability could give you a right quotient, you should consider that as a very remarkable fact. And then the next thing is you want to prove the good quotient doesn't just exist, but it's actually compact. So here I say proper, but it's compact. And then you want to prove it's a projective variety. So there is some ample lie bundle. So that's a plan. And unfortunately, all of this now is a theorem. So actually, we can consider, we fix this numerical invariance, and we consider all the K semi-stable one. There is a, as I said, there is a finite type Artin stack to parameterize this. So again, let me just emphasize, if you want to get a stack, you can replace this K semi-stable by many other conditions. So the fact that you get a stack is not, I mean, you have to prove it. It involves like deep Bayesian geometry theorem, but somehow the formal stack is kind of a soft condition, and you can change this condition a lot. However, the really subtle condition is that this stack meets a good modular space. So in other words, this quotient indeed has a good quotient modular space. And precisely this space, the same point of this space, corresponds to the Kähler-Einstein Fano variety. So up to this point, we finish our project of parameterize all the Kähler-Einstein Fano varieties. It's precisely parameterized by this good modular space. And then, as I said, we prove it's proper, so it's compact. So in other words, any degeneration of Kähler-Einstein Fano variety, there is Kähler-Einstein Fano variety as a limit, which is a unique limit. And also the same lie bundle is actually ample on this. So again, I want to explain a little bit more about how one can prove the good quotient exists. So as I said, for stack have a good modular space is a subtle property. But what's good modular space? So basically, locally, eta locally, or you can think about analytical locally, this map from X to X is basically covered by this kind of map that when you G acts on some like reductive group G, acts on some like a fine scheme, a fine variety, and then you just take the invariant ring. So here, this thing is just the Hilbert Northern times invariant theory. So basically, the good modular space just say that your stack to space mobilism is locally covered by this very classical object. So, and then the question is when a stack has such good modular space. And 2018, Harper Leisler, and Henlos, they developed a very useful valuative criterion to check that as long as your stack satisfies those criteria, then it has good modular space. So in our setting, to apply the valuative criterion, it's equivalent to prove that if I have a family of Fano varieties, I have an equivalent family of Fano varieties over a puncture surface. So here, there are two types of surface you have to check. The first one is just a pointed curve times like a say, with the say star acts on the second factor. And now there's one special point, which is a point times 0. So now if I have a Fano semi-stable family of semi-stable over this puncture surface, I want to prove I can actually fill in the limit. I can prove that there is always a limit exists. And the second type of surface is now is slightly more complicated. It's again the puncture curve. The curve is, the point is given by pi is equal to 0. And then times the surface, you consider the locus st equal to pi. And the action is 1 with weight 1, 1 with weight negative 1. And then you prove that if you take out the 0 here, in this picture, if you have a semi-stable family, K semi-stable over the puncture surface, again, you can fill in it such that you can construct a family of semi-stable surface over the entire surface. So actually, an interesting consequence of the second fill-in problem is that actually implies your any closed point on your stack, the automotive group is reductive. So particularly this implies the Matsushima theorem, but it's completely algebraic. So if I have a k polystable Fano variety, this the automotive group is reductive. So some other progress results which I want to mention here is that we want to prove the same line bundle is positive. This line bundle was first introduced by Tian. I think Tian had some like an analytical reason to believe that this line bundle should be positive on the modular space. But this was completely proved algebraically. So using some like Hadar-Nishimura filtration of the base and connect that with the K stability. And so also we have some like a local singularity theory and the K and the stability on singularity. So basically this was built on some notion introduced by Chili called the normalized volume. And we basically show that for every KLT singularity, any such singularity, there exists a unique two-step degeneration, equivalent degeneration to a rich flat cone. So here, of course, we prove some algebraic statement. We degenerate to something which is algebraic, and then one can prove that algebraic object has rich flat cone, rich flat structure. And also, you can do a similar story for instance, for the H functional. And so that just say that there exists a unique Kähler-rich soliton for any Fano variety. So when the Fano is smooth case, we know that we can run the so-called Kähler-rich flow. And if you take the limit, that will give you some like Kähler-rich soliton. But again, if you want to do the analytical theory, smoothness assumption is needed. But but if you want to just do the algebraic theory, then we can do everything algebraically without any smooth assumption. So this actually might lead to some like a modular understanding of general Fano variety without a semi-stability assumption, but that's still under development. So the last part of my talk, I want to mention some results on K-stability for explicit Fano variety. Because now we have this general theory of modular space and of stability, we want to ask what are actually K-semi-stable one? Because that's actually a very subtle question. So the general goal is basically, we have tons of examples of explicit Fano varieties. We want to say that are they K-stable? So if they are, what's their modular look like? What's the limiting point parameterized? You can ask all these kind of questions. But to illustrate how little we understand this, even for smooth Fano hypersurface, we don't have a completely understand. So we know that for smooth Fano hypersurface, a Zariski open one, so there is a Zariski open set of smooth Fano hypersurface. For points, there is a Zariski open set of the space parameterized Fano hypersurface. Points on that Zariski open set parameterized Fano K-stable Fano variety. In other words, we know general Fano hypersurface is K-stable, but we don't know every smooth one is Fano stable. And there are some other construction of Fano manifolds. For instance, we have a completed classification of three-dimensional Fano manifolds. And you can ask, how many of them are stable, how many of them are not? Another interesting example is the modular space of stable vector bundles on curves. So actually, although there are still lots of things to work on, we actually do have some better understanding than a few years ago. So we actually prove, at least for some degree, we can completely prove all of the smooth ones are K-stable for hypersurface. So this is using the estimate of some delta invariant. This delta invariant, which I said at the beginning, which can characterize the K-stability, can be approximated by some delta M. But the delta M looks like some kind of log threshold, which Bayesian geometers has some way to estimate it. And in particular, Arban and Zhuang, they invented a new method to cut things to lower dimensions. And to apply their method to hypersurface, they prove that in this kind of range, that D is, so in other words, the D is pretty large. So it's close to, remember, Fano means D is less than n plus 2. So, but now if D is less, but not too less, then actually we know all smooth ones have a Kähler-Einstein. So I think before their result, Fujita proved the case when D is equal to n plus 1. But that proof was using tensor alpha invariant, so it was like still along the more traditional approach. But this result is really use the full power of the new method. And also Chertsov and many others, they studied, as I said, they studied this Mori-Mukai classification of all the Fano threefolds, and they basically made lots of progress on understanding them. And another approach is to use like a moduli method to, basically we want to construct the moduli space. We give a explicit description of what the moduli looks like, and using this way to prove the case stability. And in surface case, I mean, this was done earlier. Now we understand the cubic threefold and the cubic fourfold. I mean, this approach actually, we have less examples because you really have to understand the entire moduli. However, there is a word crossing method to study this. So basically, if I have some variety y, I can naturally realize it has a hypersurface in some Fano variety x. So even a general type hypersurface, but if it's hypersurface, it's Pt into Pn, so it's still a Fano variety. And satisfy this property. Then I can consider the moduli space of this pair, x, y, t, and I have this coefficient. So if this coefficient is very small, then that means this pair is still log Fano pair. So I can still study the case stability for this pair. But if then this pair is large, then this larger than this threshold, then we have this Collat-Shiffer-Baron's approach to construct the moduli. So then when you move this coefficient C, you basically get lots of word crossing. But there is the most interesting one is when T is precisely 1 over A. So then, in other words, this moduli space is, this pair is log Fano. So we don't have a general theory for moduli of log Fano pairs. So when you work on examples, you can construct the explicit moduli space to parameterize the log Fanos here, but we don't have a general theory. So this is something I think was, again, under development. So let me stop here. Thank you.